This is the second of the 4 videos in which we will be talking about the presentation layer of computer networks. In our first video on the topic, we looked at the transmission of characters. And in that lecture, we realized that one of the major limitations of the early codes was their inability to transmit truly universal characters, to make provision for all the character sets that are in use in the world. Today's lecture will rectify that by looking at a code that can indeed be used for international transmission, Unicode. The challenge was to develop a code in which all characters used in all current languages could be represented. Perhaps we could even represent codes for characters that were used in alphabets that no longer existed. And there were other symbols that we may want to represent as characters. The name of the code that was developed was Unicode. As the name indicates, this was to be a universal code. It was to be a union of all the various codes that existed for all the languages. And they even introduced a nice little mathematical symbol. The mathematical symbol union with a little plus in there, symbol that is often used to indicate that various sets have to be unified, the union of various sets. So there were obviously a couple of challenges for this code. One of the challenges was how long should it be? Initially it was thought that 16 bits would be sufficient. With 16 bits, one can represent 65,000 characters. However, it turned out that 16 characters or 16 bits were not enough. We needed more. Exactly how much more? Well, let's leave that question for a little bit later. At this stage, let's quickly look at Unicode to get some feeling for what it is about and how one would use it. So let's look at the web page to look at what Unicode looks like. And one of the easiest websites to explore it is unicode-table.com. When you go to that website, you will see a couple of character sets that are displayed. But I really want to look at the code at this stage. So what I'm doing is I'm selecting the Unicode tab. So what you can see on this page are a couple of blocks or character sets. And you can see the range of every block that is indicated, the numbers that have been assigned to characters in that block. For example, the control characters range from 0 to 1F, or in decimal from 0 to 31. Then you can see basic Latin characters from 32 right up to 127. And then there's a Latin 1 supplement and so on. And range of other alphabets, Cyrillic, Armenian, Tahana, if that's how one pronounces it, Mandaic. I didn't even know there were languages like those, but the character sets are all included in this list that goes on and on and on. I'm not going to scroll through the entire list right now, but what I want to do is to look at some of the character sets. And the first one we're going to look at is basic Latin. And for basic Latin, you can see from this web page that there are 96 characters in this set. You can see some punctuation marks, special characters like a $sign and so on. And you can see the digits. You can see uppercase alphabetic characters. You can see lowercase alphabetic characters. And that's it. And that's where it stops. Now, if you've looked at an ASCII table after the previous video, you will realize that what we have here is plain simple ASCII. So ASCII, without the control characters, have been encoded in this particular block. If we go back to the control characters, then you can see that they are also characters that we've previously spoken about. There's a null, there's an SOH, the start of header, STX, start of text, and so on. You can even see number 7 there, the bell that we also mentioned previously. Now, if I click on bell, then that will tell me that the code for bell is 7. First thing to note there is that rather than using that special union symbol that they designed for Unicode, or chose for Unicode, is that they tend to write it, and this is a very standard way of doing it, they write it as U+. So something that can be written in ordinary ASCII, and then the code for bell, which is 7, so U+, and then they write down 4 hexadecimal digits. 4 hexadecimal digits, every digit would take up a nibble. So the 4 digits that they use tend to suggest that 16 bits are used. But if you look at some of the other characters later on, you will see that it's not always 7 characters. You can also here see quite a couple of characters that quite a couple of ways in which this can be represented, for example, in HTML and so on. And a little bit later, you see an encoding scheme, UTF-8 and UTF-16BE and UTF-16LE. We're going to talk about that in just a moment. One of the things that one can do with this particular website is to search for a character, because every character has a name. You can see this bell character, the name is bell. So if I want to find the code for that particular code that is used to mark Unicode, I can, in the character tag or in the search block, look for all the characters that show or that are represented or that are possible to represent. And if you look down at the bottom of the things that are suggested, you may see that there is a multi-set union. So all of these alphabets in this particular case that are combined. If I were to select that option, then I will get the code for it. It is multi-set union, it is used in Z notation, and the code for it is Unicode, so U+, and then 228E. And that is the particular representation for that. Yet again, you see other ways in which it can be represented as HTML and so on. Not going to look at that in detail. But down there, you get the other representations again, UTF, and you can see UTF-8, UTF-16, and UTF-32 that are represent or that have different variations. Perhaps when we started or when we opened this particular website, you may have noticed that one of the popular blocks right now happens to be one that is useful to talk about viruses and so on. So if we click on that particular one, you will see that in that block we have quite a couple of emoticons. So emoticons are represented as characters. The first one in that block that looks like a coronavirus is actually microbe. And there is the code if you want to display that on a screen or print that out. One of the things to notice here is that its code is U plus and then 1F9A0. So not the 4 hex digits that we had previously, but 5. So whereas the 4 would have suggested the 16-bit encoding, here the 1 definitely takes us to something beyond that. So let's talk about the representations that we've mentioned, those UTF representations that you see at the bottom of every character. The problem with Unicode is that it requires quite a couple of bits to represent a character. And that means you can communicate slower if you use it. You can store less information on a disk and so on. So we need some more economical way to represent it. What we're going to do is we're going to use a variable length instruction set or variable length representation. And that's a notation that you're quite familiar with. In Morse code, for example, you probably know that the characters that are used very commonly in French have a very short representation, whereas the characters that are uncommon, again in French, have a long representation. Now, what we want to do is, for a given language, we somehow want to represent the characters that are commonly used in as short a possible manner, and the characters that are uncommon, those we can assign to much longer codes. So what we have is a sequence of numbers that we want to use. Perhaps I should have started at 0, it doesn't matter. And I want to go down to some big number, however many characters I want to represent. Now the Unicode characters are also numbered. Again, I should have started at 0, but for this example, starting at 4 and then going to the very last Unicode character. It's possible that the short numbers are already good enough for what we want to do. But in general, we want some sort of a mapping function. And we want to say, if I write 1, then I actually mean that character, one that may require a much longer code. And if I write 2, then I may require or actually mean that character. Whereas if I write down a very long number, I may actually be indicating something that is not particularly useful for me, and that's why I'm willing to use a long number for it. So what we need is some form of encoding that maps the small numbers to the letters that we want to use frequently in our language. Now, if our language is one that is based on the Latin alphabet, then we will use a code or encoding scheme that is known as the Unicode Transformation Format, UTF. UTF was designed with different versions available. The most common one by far is UTF-8. UTF-8 is one that assumes you probably want to work in multiples of 8 bits, or you want to work in bytes, as we would nowadays probably refer to it. So you're going to use either 1 byte or 2 bytes or 3 bytes and so on. And that's the one that we're going to talk about most. There was also one that was conceptualized. In fact, if you go and look at the website, you will see that there are different variations of that one, and it is indeed in use, although not very often, UTF-16. And that's one that assumes you want to work in, let's call it, double bytes. So you will either use 1 double byte, 16 bits, or you will use 2 double bytes or 3 double bytes to give you 2, 4, or 6 bytes to use. So we're not going to talk about that one very much. Also, if you look at the options that are available, there's a UTF-32 that works in 32-bit words, one 32-bit word or two 32-bit words, and so on. Again, we're not going to look at that in detail. The one that we want to discuss is UTF-8. So the way that UTF-8 works is, as we said a moment ago, that you want to use 1 byte or 2 bytes or 3 bytes or 4 bytes, however many you need. Hopefully the shorter ones for the common characters and the longer ones for the characters that are uncommon. And to do that, one needs to indicate in the very first byte how long this entire sequence is going to be. So when somebody looks at the first byte, they need to know that this byte plus the next 2 bytes make up 1 character. And a very common scheme in computing works as follows, and you will encounter that again in future contexts. But the idea is that the starting bits of a byte will indicate the length. So the usual pattern is to start a byte with 0, and then to say the next possible value starts with 10. So that gives you an indication that the second, or it clearly distinguishes the second option with the first option. And then the next option starts with 110 and 1110 and so on. And by counting the number of ones until you get to the first 0, you know which version or which option you are dealing with. So the typical thing would have been to use these for different lengths. In other words, 0 would indicate 1 byte, that the starting pattern 10 would indicate 2 bytes, and so on. However, in Unicode, they did it somewhat strangely by saying a 0 would indicate that your entire character occupies 1 byte. And then they skipped the 10, and the 110 would indicate that the entire character occupies 2 bytes. And then the 1110, 3 bytes, and from there on it just follows the natural pattern. The 10 was used or is used to indicate a continuation byte. So what this means is if you, for example, have a character that consists or for which you need 3 bytes to represent it, the 3 bytes will be sitting next to one another. To indicate that you are using a 3-byte sequence, you can see from that option that we are going to indicate it as 1110. That means we've used up 4 bits, and in a byte that means we still have 4 bits left to indicate what we want to represent. But very importantly, whereas this byte initially tells us that we are going to use 3 bytes for the entire sequence, the next bytes are marked as continuation bytes. So they have this continuation character to start out with, which means we have 6 bits there left and 6 bits there left. So in the end, if we're using a 3-byte sequence to represent our actual value, we have 4 plus 6 plus 6, 16 bits to indicate exactly what we mean. So suppose we want to represent the character bell. You already know the Unicode value of bell is 7 hexadecimal. So written out in binary, it means that 7 in hexadecimal or decimal is simply 111. Now we can easily represent that in a single byte. So the Unicode representation of bell would be a 0 to indicate that it is a single character, a single byte for this character. We will have 111, means we've used 4 of the bits. We just have to pad with 1, 2, 3, 4 zeros. As a next example, let's look at that union of sets character again. You may recall that the Unicode representation for that was 228E. To convert that or to represent that in UTF-8, we will unpack the bits, and the E will obviously be 1110. The 8 will be 1000. The 2 will be 0010. So all of those unpacked as nibbles. But this initial 2, this leading 2, we will simply unpack as 10. We omitting the leading zeros because there is no reason to make this character longer than it should be. In fact, if we make it too long by adding zeros, we may need a longer representation, and that longer representation would be incorrect. Just looking at the data, the bits that we have to represent, that we have to encode now, there are 14 bits, and we know there's no way that we're going to fit that into a single byte. So we know that a number of these will be trailing bits. So for trailing bits, or trailing bytes rather, for trailing bytes, we know that we will have the bit sequence 10 to indicate that it is a trailing byte, and then we will be able to pack 6 bits into that. So the first 6 bits that we will be able to pack into a trailing byte will be those 6 bits. The next 6 bits that we will be able to pack into a trailing byte will be those 6 bytes. And then I'm not going to spend too much time to convince you that 10 at the beginning will indeed fit in the leading bit. So let's then pack this into our 3 bytes that we will need for or to represent this particular character in UTF-8. Just as a quick reminder, if we use a 0 in our leading bit, that indicates that the entire sequence will be 1 byte long. If we use a 10, the entire sequence, well, it doesn't tell us anything because that's used for continuation bytes. 110 will be used to start as 2-byte sequence, and 1110 will be used to start a 3-byte sequence. So that's what we are dealing with here. So in our leading bit, leading byte, we will say 110 to indicate that we're going to use a 3-byte sequence. And the 10 that we have there have to be packed in there, so that becomes 10. That means we've used 6 of the 8 bits. We have to pad it with zeros. The second sequence will be a trailing byte, so we will mark that as such, 10, and then the sequence to pack in there would be 001010. Those 6 bits that formed the second trailing byte. And then the third byte will have a 10 yet again to indicate that it is a trailing byte or trailing octet, and those 6 bits will be packed into the remainder, so it will be 001110. And to translate this to hexadecimal, because typically we represent the UTF characters in hexadecimal, we will split them into nibbles, and that nibble would be E, that nibble would be 2, that nibble would be 8, that nibble would be A, that one would be 8, and that one would be E. Simple binary to hex conversion, which means our UTF representation would be the bytes E2 followed by 8A followed by 8E. Now, suppose you are in Japan, then you will want to use a different kind of encoding, something that moves the Japanese characters to the start of the list and move, let's say, the Greek alphabet to the end, because we may not be particularly interested in them. So if you want to represent characters in Japan, you're not going to use UTF. UTF puts the Latin characters at the front, and the Japanese characters follow quite a bit later. So what you would rather use is an encoding that is known as ShiftJIS. JIS, Japanese Interchange Standard. So that will take the Unicode characters, assign a different sequence to them, in other words, different mapping to them, and then you will be able to map the Japanese characters to small numbers, map the characters that you are not particularly interested in to long codes, and then the various characters will be represented using the same principles that we've seen in UTF. But they will have a very, very different representation in ShiftJIS. Recall that what we said in the previous video, the first couple of characters, in essence the ASCII character set, is used for commands. So those are going to be used frequently during data communications, and they will keep their shortcodes. However, just beyond that is where you're probably moving your Japanese or your Chinese or whatever is the common language in your context. In this and the previous video, we spoke about the presentation or representation of characters. In the network context, we clearly want to talk about protocols rather than just presentations. But having spoken about presentations or representations, we can, in the next video, move on to a way in which this all becomes part of a protocol, and where this functions much more like the typical protocols that we will see or have seen on other layers of the protocol stack. See you in the next video.